Welcome to the today's class. Today we are going to deal with Brayton cycle with non-ideal components. In the gist, what we have covered till time, we have covered the ideal Brayton cycle with intercooling, Brayton cycle with heat exchanger, Brayton cycle with reheating. We have seen their advantages, why we shouldn't have Brayton cycle with intercooling, why we should have heat exchanger, and why we should have reheater. Every component has its own advantages and disadvantages. Further, we have also seen that if we integrate everything, like there is a single power plant with everything together, like heat exchanger, intercooler and reheater, then what would happen? Then how to do the cycle analysis, that we have seen. But now in today's class we will be seeing that if we are having the non-ideal components as part of a Brayton cycle, the fact to be understood over here is that basically we have four components in Brayton cycle. One is compressor, other is turbine, then we have combustion chamber, and then we have heat loss. So, or in case of closed cycle we have pre-cooler. But within that we are having two components which are rotary machines, and those two components are compressors and turbines. And now if these two components are non-ideal, then how would be the cycle analysis? This is the topic of discussion for today's class, and then we would see to solve some examples. So let us see if we have a Brayton cycle with non-ideal plants, non-ideal components. So let us first consider the TS diagram as what we already always consider. So we have T axis and we have S axis. So the process, initially what we would try is all the processes what we already know, those processes we will plot for. So we will initially plot for ideal cycle. So this is 1 to 2 is compression. So but we will not say now 2, we will say it as 2 dash is a compressor. Then 2 to 3 is heat addition process. Then 3 to 4 is a expansion process in turbine. So this is what we have already seen, but now we will not say it as 4, but we will say it as 4 dash. So we have 1, 2, 3, 4 as our cycle. Now having said this as our cycle, we will see now if we are having non-ideal components. So suppose compressor is non-ideal, so that means we are not going to reach the point 2 dash after the process of compression. So we mean that what are the reasons of being non-ideal? The major reason what we will consider over here is a friction. So frictional losses are there in the case of compressor, due to which compressor would not let us go to the point 2 dash, and then we would go to some other point and let it be some other point, it is 2. So instead of growing from 1 to 2 dash, we went to from 1 to 2. We know that process 1 to 2 is a real process, it is an irreversible process. So 1 to 2 is showed by a dotted line. So as what we know, 1 to 2 is a real compression process, and 1 to 2 dash is ideal compression process. But one point we have to keep it in mind, that pressure 2 is equal to pressure 2 dash. We did not get landed in a different pressure condition. So pressure at 2, which is a static pressure at 2, is equal to static pressure at 2 dash. So this is what we have achieved by the still having non-ideal component, which is a compressor. But then when we say that we have compressor which is an ideal, we mean that compressor thermal efficiency is 100% for ideal. But then what is the definition of compressor efficiency? So compressor efficiency can be defined as ideal work input to real work input. We have to keep one point in mind, and rather remember that compressor is a work input machine. So here we are giving some work input. Ideally we always would need less work for input than the real condition. So ideal work being less, what we call it as W dash C divided by WC. But we know that W dash C is always less than WC, so efficiency is always less than 100%. So in real case we need to supply more pressure to get same pressure at the outlet of the compressor. So practically we are supplying more work input to the compressor to get same pressure, but ideally we would need less work input to get the same pressure. In that aspect we know that compressor efficiency, we know work input to the compressor Cp into T2 minus T1, this is real work, ideal work, then Cp into T2 dash minus, so we have T2 dash minus T1 and T2 minus T1. So this is ideal work and this is real work. So basically we would also have written it as H2 dash minus H1 divided by H2 minus H1. This is the enthalpy based formulation for the work. We directly wrote, considering the gas to be a perfect gas which we are having, and we are also assuming that Cp and Cv is not function of temperature. So we are having calorically perfect gas as an assumption if we go from here to here. So compressor efficiency would ultimately become for calorically perfect gas as H2 dash minus H1 divided by H2 minus H1. When we will deal with the examples, then we would understand that compressor efficiency would be a known parameter for us. And parallelly we also know that pressure ratio is also a known parameter for a compressor. So pressure ratio is known, compressor efficiency is known, and then we would also know what are the inlet conditions of the compressor. So practically what we would be knowing is compressor efficiency, pressure ratio, gamma and T1. These things, or P1, these things would be known to us. Having these things known, our objective over here is to find out what is T2 dash. Since we are going to do some more derivations based upon the non-ideal components. So we know that for process 1 to 2, we know that P2 dash is equal to P2. This is known to us. And then now our objective is to find out what is T2. So, but we know that T2 dash upon T1 is equal to P2 upon P1 bracket raised to gamma minus 1 upon gamma. So this is for the point 2 dash, which is an ideal point. So we know that T2 dash upon T1 is Rp raised to gamma minus 1 upon gamma. So we know that T2 dash is equal to T1 into Rp bracket raised to gamma minus 1 upon gamma. This we have already seen. But now we know efficiency, so we are supposed to find out T2 dash or T2. So we know that efficiency is equal to T2 dash minus T1 divided by T2 minus T1. So here we can take T1 as common, then what we can get is T2 dash upon T1 minus 1 divided by T2 upon T1 minus 1. Okay. So what we can write as T2 upon T1 minus 1 is equal to 1 upon compressor efficiency into T2 dash upon T1 minus 1. But we know T2 dash upon T1 is equal to Rp raised to gamma minus 1 upon gamma. So this is equal to 1 upon compressor efficiency into Rp raised to gamma minus 1 upon gamma minus 1. So we have T2 is equal to T1 into 1 plus 1 upon compressor efficiency into Rp bracket raised to gamma minus 1 upon gamma minus 1, and then all brackets complete. So this is the expression for calculating temperature at the exit to the non-ideal compressor. So here all the quantities are known to us on the right hand side. So we can find out T2, which is the actual temperature at the outlet of the compressor. So now we will go with the next point, which is the non-ideal turbine. So 3 is known to us, by the way, which is a Tmax point, or which is the point after the combustion chamber. We assume combustion chamber or heat addition and heat rejection processes are ideal, so we have to just work out with turbine. So in the case of turbine, what we will have, again we will try to draw the TS diagram for the next slide. So we have T axis, we have S axis, then we have 1 to 2 compressor, then we have 2 to 3, and then 3 to 4. But what we are seeing now is non-ideal components. So for non-ideal components, we have 1 to, basically this is 2 dash, so 2, this is 4 dash, so this is 4. So this is the non-ideal turbine case. So in case of non-ideal turbine, now again we have known that the turbine efficiency for non-ideal ideal case will be again 100%. So again we have to define what do we mean by efficiency of turbine. Again here we are considering the losses due to friction in the case of turbine. So it's an isentropic efficiency of turbine. So turbine efficiency, if we define in terms of enthalpy, then it will be H4 minus, H3 minus H4 divided by H3 minus H4 dash. So practically it means actual work done divided by ideal work done. So it means Wt divided by Wt dash, and then we know that Wt is always less than Wt dash. We again would remember that turbine is a work producing machine. So in case of work producing machine, we always would need the we always would get lesser work output than the ideal case. So turbines would have non 100% efficiencies. Again, if we try to again assume the gas to be calorically perfect, then we will have turbine efficiency as Cp into T3 minus T4 divided by Cp into T3 minus T4 dash. One more point to be remembered here, that as in case of compressor, we did not land in different pressure. The pressure at 4 dash and pressure at 4 is same. Turbine exit is having same pressure, whether it is ideal expansion or non-ideal expansion. So we have the expression for efficiency of turbine is T3 minus T4 divided by T3 minus T4 dash. Now for the process 3-4, the same thing what we did for earlier case for the process 3-4. We know that P4 is equal to P4 dash, but for again finding out the temperature T4, we know that we are knowing turbine efficiency, we are knowing pressure ratio, we would know T3, which is a Tmax by some means, then we know gamma. So these are things which are known to us. So now what we can find out, is turbine efficiency is equal to T3 minus T4 divided by T3 minus T4 dash. Our objective is to find out T4. So T4 minus T3 is equal to turbine efficiency into T3 minus T4 dash. So T4 is equal to T3 minus, one second, so this is equal to T3 minus T4 dash. So we have T3 minus T4 is equal, so efficiency is equal to T3 minus T4 divided by T3 minus T4 dash. So we want to find out T4. So for that, T3 minus T4 is equal to efficiency into T3 minus T4 dash. So T4 is equal to T3 minus efficiency into T3 minus T4 dash. So what we would have is T4 is equal to T3 minus turbine efficiency into T3 into 1 minus T4 dash upon T3. But we know that T4 dash upon T3 is equal to P4 upon P3 bracket raised to gamma minus 1 upon gamma, and that is 1 upon Rp bracket raised to gamma minus 1 upon gamma. So what we ultimately would have is T4 dash T4 is equal to T3 minus T3 into turbine efficiency into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So T4 is equal to T3 into 1 minus turbine efficiency into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So this is the formula for finding out temperature at the exit of the turbine. Here we know all the quantities, like again we know what is the pressure ratio, what is the gamma, what is the turbine efficiency, and what is the T3, which is T max. So having known this, we can find out the actual corner properties, which are temperature and pressure. So now we know what is turbine work output. Turbine work output is TCP into T3 minus T4. So T4 is known to us. Similarly, compressor work is Cp into T2 minus T1, again T2. New formula for T2 in terms of compressor efficiency is known to us. Having known these things, we should now find out what is the optimum condition for the maximum work output in case of the compressor and turbine based plant where both are non-ideal. So having said this, we should find out W net. So let us work for this. So we are now having non-ideal plant where we have turbine and compressors with non-ideal efficiencies. So what we have, this is a turbine, and then what we have, this is a compressor. 1 to 2 dash, 1 to 2, 1 2 to 3, 3 to 4, and 3 to 4 dash. So these are the processes in case of non-ideal, and we saw that compressor work is Cp into T2 minus T1 and turbine work is Cp into T3 minus T4. Now we are supposed to find out W net. We know that W net is Wt minus Wc. So W net is Cp into T3 minus T4 minus Cp into T2 minus T1. So what we have is Cp into T3 minus T4 minus T2 plus T1. So W net is equal to, known quantities are taken out, so we have T3 upon T1 minus T4 upon T1 minus T2 upon T1 plus 1. Here Cp is known to us, T1 is known to us. Practically T3 is also known to us. So we know that we have used T3 upon T1 as beta, and then that is constant or that is known. Similarly Cp and T1 are also known. So we are working out the W net formulation or constraint for maximum W net with these fixed things. So W net is equal to Cp T1 into beta minus T4. We can write T4 by T1 minus T2 by T1 plus 1. But what we know is T4 is equal to, from last slide we can take it, T4 is equal to T3 into 1 minus eta T Rp raised to gamma minus 1 upon gamma. So this is T4. Similarly T2 is equal to, is known to us, T1 into 1 plus T1 into 1 plus compressor efficiency Rp raised to gamma minus 1 upon gamma minus 1. Upon compressor efficiency. So these two things are known to us, so we can use them to find out the W net. So W net is equal to Cp T1 into beta minus T4 by T1. So that will be T3 by T1 into 1 minus eta T into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. Then we have minus T2 by T1. So we have 1 plus 1 upon compressor efficiency into Rp raised to gamma minus 1 upon gamma minus 1 plus 1, then bracket complete. So this is basically T4 by T1, and this is practically T2 by T1. Then now we need to differentiate this formula with respect to Rp, but before that we know that W net is equal to, the quantities with constants can be separated or known quantities can be separated. So we have Cp T1 into beta minus beta into 1 minus eta T 1 minus 1 upon Rp raised to gamma minus 1 upon gamma, bracket complete, minus 1 minus 1 upon compressor efficiency Rp raised to gamma minus 1 upon gamma minus 1 plus 1. So having said this, we know that beta is a constant. So since beta is a constant, its differentiation with respect to Rp will be 0. So here we have to keep in mind that apart from above things, eta c and eta t are also known. Having these things known, we can now differentiate d w net by d Rp, and then we can equate it to 0. So having said this, what we will get, so this quantity is a constant, so Cpt1 is a constant, its differentiation would be 0, so we can neglect that, and then we will have this also to be 0. So we directly would end up in this way, Cp d Rp of minus plus beta into eta t into 1 minus 1 upon Rp bracket raised to gamma minus 1 upon gamma minus, so this differentiation will be 0, so minus plus, so d by drp of 1 upon compressor efficiency into Rp raised to gamma minus 1 upon gamma minus 1 plus 1, and then this equal to 0. So having said this, we can differentiate it, and then we can find out that within that these first two quantities, when we multiplied with 1, they will have their differentiation to be 0. So what we ultimately would have is minus d upon drp of 1 minus Rp raised to gamma minus 1 upon gamma, and then this quantity would be multiplied by eta t plus and beta plus, then we would again have differentiation will be 0 for this one, so we will have d upon drp of only this quantity, which is 1 upon eta c into Rp raised to gamma minus 1 upon gamma, and this term would be equal to 0. Having said this, we can differentiate it and then find out what is happening. So its differentiation will be beta minus beta eta t into minus gamma minus 1 upon gamma into Rp bracket raised to minus gamma minus 1 upon gamma minus 1. So this is the differentiation of this term, and then differentiation of this term would lead to plus 1 upon eta c into Rp into gamma minus 1 upon gamma into Rp bracket raised to gamma minus 1 upon gamma minus 1 equal to 0. So the term in the bracket, which is gamma minus 1 upon gamma, would get cancelled. So what we would have is beta into eta t into Rp bracket raised to minus gamma minus 1 upon gamma minus 1 is equal to minus 1 upon eta c into Rp bracket raised to gamma minus 1 upon gamma minus 1. So we have beta eta t eta c equal to Rp raised to, here we will have gamma minus 1 upon gamma minus 1 plus we will have gamma minus 1 upon gamma plus 1. Okay. So, there is a slight mistake, here it is 1 plus 1 upon eta c. So, here it should be 1 plus 1 upon eta c. So, here it will be minus, here it will be minus, so here it will be minus accordingly, and then this would lead to minus over here, and then it would lead to plus over here, and then we will have beta eta t eta c is equal to Rp raised to 2 into gamma minus 1 upon gamma. So, Rp raised to gamma minus 1 upon gamma is equal to square root of beta eta t eta c. So, this is the constraint on the optimum pressure ratio for the maximum network in case of non-ideal components of the Brayton cycle. So, if we have non-ideal components of the Brayton cycle, we would get ultimately the pressure ratio is equal to square root of pressure ratio raised to gamma minus 1 upon gamma is equal to square root of beta eta t into eta c as a constraint on optimum pressure ratio. So, such pressure ratio which satisfies this is called as optimum pressure ratio. As what? We would remember that if these efficiencies are 100%, then we had seen that for ideal cycle we had Rp optimum bracket raised to gamma minus 1 upon gamma was square root of beta. So, we just got an additional components with beta as eta t and eta c. So, here we practically end the part what we were talking about as if we are having non-ideal components. So, we have to keep again a point in mind that the things won't change except what we will have is a turbine and compressor efficiencies. So, those turbine and compressor efficiencies will be used to find out the temperature at the end of the turbine or temperature at the end of the compressor. Rest of the things would remain same. There is one more point to note, that now heat addition would not start from 2 dash, but it will start from T2. So, heat addition will be Cp into T3 minus T2. Similarly, in case of heat rejection, it will not start from T4 dash, but it will start from T4, then Q out is equal to T4 Cp into T4 minus T1. So, efficiency would accordingly change. So, efficiency would be 1 minus Q out upon Q in. So, 1 minus Cp into T4 minus T1 divided by Cp into T3 minus T2. So, we know now T3, we know now T2, we know now T4 and we know T1. So, accordingly we can find out efficiency. So, this is how the chapter or the part for non-ideal components is. Now, we will see some examples. We will here see how to solve the example or what are the things which would be given in general in an example. So, an example says that there is a gas turbine which operates on a pressure ratio 6. The inlet air temperature to the compressor is 300 Kelvin and the air enters the turbine at 577 degrees Celsius. If volume flow rate of air is 240 meter cube per second, then calculate power output in megawatt for the gas turbine power plant. So, what is given to us? So, what is given to us is given in the example. In the example, we are given with Rp and that Rp is equal to 6. First, we should always draw the TS diagram. In this example, since we are not given with turbine and compressor efficiencies, we can assume turbine efficiency and compressor efficiencies as 100%. So, they are 1. So, for us we are working with ideal gas turbine power plant 1, 2, 3, 4. So what is given to us is Rp. So we are knowing P2 by P1 is equal to Rp is equal to 6. So we parallelly know the inlet air temperature to the compressor, means we know T1 is equal to 300 Kelvin, and then we know turbine entry temperature, which is T3. T3 is equal to 577 degrees Celsius. So it is 577 plus 273 Kelvin. So I am just explaining the process. What we are given is volume flow rate, and volume flow rate is 240 meter cube per second, and we are supposed to find out what is W net. But the usual formula of ours would lead W net in kilojoule per kg, but here we are supposed to find out W net in megawatt. So this we have to remember. So what we can do? We know that W net is equal to Wt minus Wc. So we know that Wt is equal to Cp into T3 minus T2 minus Cp into T2 minus T1. We again should know that Cp for air is 1.005 kilojoule per kg Kelvin. This is information which either would be known to us or would be given to us. So turbine work is T4. So turbine work is T3 minus T4, and compressor work is Cp into T2 minus T1. Then for us, we don't know what is T4 and we don't know what is T2, but we know T2 by T1 is Rp raised to gamma minus 1 upon gamma. So we know Rp, we know T1, we can find out T2. So T2 is equal to T1 into Rp bracket raised to gamma minus 1 upon gamma. Since we are told with air, for air gamma is 1.4. So we know Rp, we know gamma, we know T1. So now T2 is known to us. Then T2 is known to us. Then T3 is also given to us as it is told. So now we just have to find out T4. So for T4 also we know formula T3 by T4 is Rp raised to gamma minus 1 upon gamma, but this leads to T4 is equal to T3 upon Rp bracket raised to gamma minus 1 upon gamma. So here as well T3 is known to us, gamma is known to us, Rp is known to us. So now T3 is known to us. Knowing T4 is known to us. So knowing T4, knowing T2, knowing T3 and T1, we can find out W net. But this W net in kilojoule per kg is known. Our objective over here is to find out what is the W net in megawatt. So here we have to multiply it with mass flow rate or volume flow rate. So what is the volume flow rate? Volume flow rate is given to us with 240 meter cube per second, but this is volume flow rate. So we have to find out mass flow rate. So for mass flow rate we have to multiply by density. So mass flow rate is equal to volume flow rate into density. Then where we have to find out density? We have to find out density at 1. So we know we will take pressure as 1 bar at the inlet, and then we know temperature 300 Kelvin, then we can find out density. So for that we will assume P1 is equal to 1 bar. So if we take P1 as 1 bar, then we know P is equal to rho RT, then knowing the pressure and knowing the temperature, we can find out density at the inlet. So we know, once we know the density at the inlet, we know volume flow rate, then we know mass flow rate. Then W net in megawatt is equal to W net in kilojoule per kg in mass into mass flow rate, which is kg per second. So this is how we can solve this example where we are supposed to find out what is the power output in megawatt. So having said this, we will see how the next example is. In the next example, we are again told that there is a gas turbine which operates on a perfect heat exchanger. So this example is with a gas turbine with heat exchanger. The inlet air temperature to the compressor is 300 Kelvin and pressure is 1 bar. Compressor outlet pressure is 5 bar and temperature is 475 Kelvin. At the outlet of the heat exchanger, air temperature rises to 655 Kelvin. The turbine inlet and outlet temperatures are 870 Celsius and 450 Celsius. Find out power output and efficiency of and compressor work. So here as well, first we will start with TS diagram. So as per TS diagram, we are at 1, 2, but 2 to 3 is a heat exchange process. Then 3 to, so we did not name it as 3, we 3, 4, here we have 5 and then here we have 6. So this is the ideal cycle with heat exchanger. So now in the given things, we are given with P1 which is 1 bar, T1 which is 300 Kelvin. We are again told that P2 is 5 bar. So practically Rp is 5, which is P2 by P1. It is given to us. But we are also given that T2 is equal to 475 Kelvin. We are told that T3 is equal to 870 degrees Celsius and T4 is 450 degrees Celsius. Okay. So keep this point in mind. T2 is 475 Kelvin, but T4 is 450 plus 273 Kelvin. For heat exchanger to operate, we always know that T4 has to be greater than T2. But we are told that T5 is 655 Kelvin, which is the temperature at the outlet of the heat exchanger. Now we are supposed to find out power output and efficiency and compressor work. Compressor work is simple to find out. WC is equal to Cp into T2 minus T1. Again, for all this case, we have to take gamma is equal to 1.4, Cp for air 1.005 kilojoule per kg Kelvin, and then we know Cp, we know T2 and we know T1. So compressor work can be easily found out. Similarly, for turbine work is also Cp into T3 minus T4. T3 is also given, T4 is also given, Cp is also known, so turbine work can also be found out. So W net is equal to Wt minus Wc. So turbine work is known, compressor work is known, then we can find out W net. But what is that we have to find out is efficiency. So for efficiency there is only one glitch, only one problem, that we have to find out Q in. So Q in is Cp into T3 minus T5 and it's not T2. That's what we have to remember, since combustion chamber entry temperature is T5. So T3 is known to us, T5 is known to us, Cp is known to us, we know Q in. Then efficiency is W net upon Q in. Thus we can find out how the different parameters of the cycle can be found out. For every case, one thing we have to remember, that first we have to draw the TS diagram or PV diagram of the cycle. Then we have to find out what are the given things. From the given things we have to find out all the corner parameters like T2, P2, T3, P3, T4, P4. Once those parameters are found out, then we can find out heat and work interaction in each process, like compressor work, like turbine work, like Q in and Q out, and then we can find out what is the resultant performance parameters of the cycle, which are efficiency, W net, like parameters. So this is the fact which we should remember, and we end here with the lectures for the fact where we were dealing with the compressor, turbine. If they are non-ideal, then how would they affect the Brayton cycle. Thank you.